Chemical properties, what can be the chemical properties of any alkane? So first of all, alkanes are inert towards acid, base, and oxidizing and reducing agent. This we know that they do not react with the acid, base, and oxidizing and reducing agent. Okay. Therefore, they undergo the following reactions. First is substitution reaction. Okay. So when one or more hydrogen atoms of alkanes can be replaced by a halogen, nitro, or sulfonic acid. Okay. So like chlorine, bromine, fluorine, iodine can be there, a nitro group can be there, and a sulfur group, SO4 negative, can be there. And halogenation takes place either at higher temperature or in the presence of diffused sunlight or ultraviolet light. Okay. So halogenation can be there at high temperature or in the presence of sunlight or in light. Okay. These reactions in which hydrogen atom of alkanes are substituted are known as substitution reaction. So like as an example of chlorination of methane. Okay. So like methane molecule is there, it is having 4 hydrogen. And when any of the hydrogen is substituted in the presence of HCl, which is, so this CH3Cl will be there. Okay. This is my chloromethane. Okay, so substitution reaction is a first reaction. Okay. Yeah, under the chemical properties, that alkane are less reactive to acid, base, and oxidizing and reducing agent. So methane in presence of chlorine gives us chloromethane. Then chloromethane in presence of chlorine gives dichloromethane. Dichloromethane in presence of chlorine gives trichloromethane. Trichloromethane in presence of chlorine is giving me tetrachloromethane and HCl. Ethane in presence of chlorine is giving me chloroethane plus HCl. Okay, this can be our CH3, CH2, ClC. It is found that the rate of reaction of alkane with halogen is fluorine, chlorine, and bromine and iodine, because fluorine is most electronegative, then chlorine, then bromine, and then iodine. Okay. So rate of replacement of hydrogen of alkanes is 3 to 1. Okay. Chlorination is too violent to be controlled. Okay. Chlorination can happen very easily. Iodination is very slow. Okay, because it is least reactive and a reversible reaction can happen. Okay. Like if iodine reacted with my methane CH4 molecules, I2 was there, then methyl iodide is formed, then it's a reversible reaction. Okay, it's a reversible reaction. It can be carried out in the presence of oxidizing agent like HiO3 and HN. Okay, so like if I have to carry out, then in the presence of nitric acid and iodic acid, I will have to do these reactions. So like methane plus iodine is methyl iodide. And this is hydrogen iodide. Okay. Then HiO3 plus 5Hi gives I2 plus H2. Okay. So if in presence of iodic acid, it is giving me iodine and water is removed. So halogenation is supposed to be proceeded via free radical chain mechanism involving 3 steps. First is initiation, propagation, and termination. So in the process of initiation, the homolysis of chlorine molecule in the presence of heat or light. Okay. So homolytic cleavage was there, one free radical with the first chlorine and second free radical with the second chlorine. Okay. The Cl-Cl bond is weaker than the Cc and Ch bond, and hence it is easiest to break. Okay. This process is known as homolysis. Okay. The Cc and Ch bonds are different. Okay. Propagation, chlorine free radical attacks the methane molecule and takes the reaction in the forward direction. Okay. So propagation is the process in which, like, if chlorine free radical is there, then it will attack towards the methane molecule and will take the reaction in the forward direction by breaking the CH bond. Like in methane, I was having 4 CH bonds. Then chlorine free radical will attack on any of the hydrogen, will take its form H and will give you HCl, and then CH3 free radical in the presence of sunlight. Okay, H nu is in the presence of sunlight. The methyl radical thus obtained attack the second molecule of the chlorine to form methyl radical. Okay. This was the first molecule of chlorine free radical. second molecule of chlorine free radical. So this will attack to this chlorine free radical and it will form CH3Cl. Okay. With the liberation of another chlorine free radical by homolysis of chlorine. Okay. But then the liberation of another free radical. Okay. There is a continuous homolytic cleavage. Okay. Then the methyl radical thus obtained attacks the second molecule of chlorine to form CH3Cl. Okay. So now this methyl radical attacks second molecule to form CH3Cl with the liberation of another chlorine free radical, and then this this methyl radical with the next chlorine. Okay, next Cl2 molecule. Now it is converted to methyl chlorine and again chlorine free radical. So chlorine and methyl free radicals generated above repeat steps A and B respectively and thereby set up a chain of reaction. Okay? This is what is called propagation. Okay. The propagation steps A and B are those which directly give principal products, but many other propagation steps are possible and may occur. Two steps are given below, like methyl chloride in presence of chlorine. Methyl chloride in presence of chlorine free radical gives methyl chloride plus HCl. Methyl chloride in presence of chlorine molecule, Cl2 molecule. It is giving me CH2Cl2, okay? CH2Cl2 plus Cl free radical. Okay. Termination step, when the chain reaction propagation step happens, the reaction stop after some time due to consumption of reactants or due to the following side reactions. The possible chain termination steps are Cl free radical and Cl free radical is giving me Cl2. CH3 free radical is giving me ethane molecule again. This methyl free radical and chloride free radical is giving me methane, methyl chloride. Okay, methyl chloride CH3Cl. Okay, so in the C product, methyl chloride, the one of the product is formed, but free radicals are consumed and the chain is terminated. The above mechanism help us to understand the reason for the formation of ethane as the byproduct during the chlorination or methylation. Okay, so it happens with the free radical mechanism in which chlorine free radical at the end of the termination forms the ethane molecule. Okay, so we can say over here that in the initiation reaction over here, when chlorine free radical was generated, and then methane molecule. Okay, methane molecule was giving us ethane molecule because two methane molecule. First of all, they are forming CH3Cl and CH3Cl. And then what is happening? Two methyl radicals are generated, which on reaction are giving me CH3, CH3, okay, or C2H6, which is ethane. Chloroethane formation we have seen, mechanism we have seen, initiation, propagation, and termination reaction for the formation of alkane molecule. Okay, so next is our combustion reaction. Okay, so combustion reaction that alkanes on heating in the presence of air or dioxide. Okay, alkane, methane on reaction with oxygen gives us carbon dioxide and water. Okay, completely oxidized to give carbon dioxide and water with the evaluation of large amount of heat, which is enthalpy of formation of this is 893 joule/1. So due to the evolution of large amount of heat during combustion, alkanes are used as a fuels. Okay. And during incomplete combustion of alkanes with insufficient amount of air or oxygen. Okay, so like incomplete combustion of alkane in presence of insufficient, oxygen was not present. Okay, or carbon black is formed, which is used in the manufacture of in filtering black pigments such as filters and as filters. Okay, so it acts as a adsorbent. Okay, so insufficient combustion, incomplete combustion due to the insufficient amount of oxygen leads to the formation of ink, printing, black pigments, and filters. Now, controlled oxidation. With related cycle and a variety of oxidation. Okay, so alkanes give a regulated supply of air or oxygen. The presence of give different products. Okay. First is alkanes usually resist oxidation with oxidizing agents such as potassium dichromate or potassium dichromate and cheminophore. Okay, so they have the and potassium di. Okay, so these are they resist, usually they resist the oxidation by these two. Okay. So like methane in the presence of oxygen is given methanol. Okay, so any alkane, if it is getting oxidized, then it is giving us alcohol. And then methane on oxidation can give us, like, the oxidation agent should be different. Like over here, we were using potassium permanganate. Okay, permanganate. This is potassium permanganate. So here we are using potassium permanganate. In first, we use the copper as a catalyst. Here we are using molybdenum. So methanol and water are formed. Ethane, on oxidation of ethane, it is giving us ethanoic acid, but manganese ethanoate is used over here. The ordinary alkanes resist oxidation, but alkanes having tertiary hydrogen can be oxidized to corresponding alcohol by potassium permanganate. Okay. So KMnO4. So 2-methyl propane, 1,2-di. Okay, so it will start from here, 1, 2, 1, 2, 3, and 4. Okay, why I'm giving this priority? Because at the second position, like I will start my numbering from here, 1, 2, 3, like this, 1, 2, 3. Okay. So at second position, there is a methyl substitution. So I cannot start from, uh, yes, I can start from anywhere. It will be the same thing, 1, 2, and then 3. So at 2-methyl propane, at first position, there is all, and second position, there is also 1, 2-dimer. In the periodic acid, or we can say potassium permanganate. So it is giving us acetone and formaldehyde. Okay. So if it is having a tertiary, like here 3 carbons has been attached. This carbon, 3 carbons are attached. Okay, first, second, and third. Okay. So this is a tertiary carbon. And if tertiary carbon, if tertiary hydrogen is present, then it can give us corresponding alcohol. Okay. So, like if tertiary, this corresponding alcohol can be oxidized to acetone and formaldehyde. Acetone is our CH3COCH3. So this corresponding alcohol is oxidized to ketone. So this group has been removed, and this CH2 here, it is C, is oxidized to double bond O, and H and H were there. This is formaldehyde and acetone. Then comes isomerization. Okay. So analkanes on heating in the presence of anhydrous aluminum chloride and hydrogen. Okay. Anhydrous means there are no water molecules, and hydrogen chloride is our HCl and AlCl3. So we can see that in the figure it is given. That this anhydrous aluminum AlCl3 and HCl is giving this N-hexane if it is reacting. So it can give two isomers. Okay. So chloride gas isomerizes to branch chain alkanes. Okay. So major products are given below. Some minor products are also possible, which you think over. Minor products are generally not important in organic reactions. Okay. So major product means which are formed in a good yield, like 90%, and minor products are those which are formed in less yield, like up to 10%. Okay. So here 2-methyl pentane and 3-methyl pentane are there. So here again Markovnikov's rule will apply. If it is going to be done in the presence of, in the absence of hydrogen peroxide. Okay. So, and H2O2 is absent. So it is Markovnikov's rule. Okay. In Markovnikov's rule, like here, the alkane will go into the carbon having less number of hydrogen. So 2-methyl pentane. And if I say over here at the third position, At the third position, 2 number of hydrogen. So second and third will always remain the same. Okay. So 2-methyl pentane and 3-methyl pentane can be formed in case of Marconi-Cox rule. Okay. So but these Marconi-Cox and anti-Marconi-Cox rules are applied in case of alkene, not in case of alkene, because against two double bond, we will look at the number of hydrogens which are present. Okay. So here in case of alkene, we cannot look at the anti-Marconi-Cox or Marconi-Cox rule. But here, 2-methyl pentane at the second position. Okay. At the second position, there can be a substitution. So pentane can be formed. And 3-methyl pentane at the third position, there can be a substitution. So if then only two isomers will be possible. Okay. Because at the third position, if I will do, then what will happen? Yes, 4-methyl pentane can be there, but 4-methyl pentane cannot be there because 1, 2, 3, 4, 5, and 6. So if we will start from here like this. So 1, 2, 3, 4. 4-methyl, if we will write, then this will be 1, 2, 3, 4. But this cannot be possible because always the priority is given to the nearest carbon. Okay, nearest to the chain. Nearest to the chain. Okay. So if I take this, so if I cannot make this 4-methyl. Okay. I have to start the numbering from here. Okay. So this will be 3-methyl hexane, not 4-methyl hexane. Okay. And at second position, we have already done substitution. Okay. So we can do dimethyl substitutions like this. So 1, 2, 3, 4, 5, and 6. Like up to this will be there. And it will be 4, 1. But then again, the same thing will happen like this. 1, 2, 3, and 4. Okay. So 2, 2 dimethyl. This will be 2, 2 dimethyl butane. Okay. Then comes aromatization reaction. So analkanes having 6 or more carbon atoms on heating at high temperature and 10 to 20 atmospheric pressure in the presence of oxides of vanadium, molybdenum, chromium, supported over alumina get dehydrogenated and cyclized to benzene and its hormones. Okay. So this was my alkane. Okay. 6-membered alkane was there. This was 7-membered alkane, so it is haptane. Methyl cyclohexane, that's 7-membered. This has formed a cyclohexane-like structure. Okay, cyclohexane, and then methyl group is attached. In the presence of chromium oxide, so Cr2O3. With the removal of hydrogen, this double bond, like over here and over here, if double bond, if hydrogen is removed, then unsaturation comes, and this is what is called toluene. So this reaction is known as aromatization or reforming. Toluene is a methyl derivative of benzene. So which alkene do you suggest to preparation of toluene? Okay, so 7-membered heptane ring has to be considered. Okay, heptane. 1, 2, 3, 4, 5, 6, and 7-membered. Okay. Reaction steam, or we can say water. Methane react with steam at a very high temperature of 1273 Kelvin in the presence of nickel catalyst to form carbon monoxide and dihydrogen. This method is used for the industrial preparation of dihydrogen gas. Okay. Methane in the presence of steam and nickel catalyst and heating at very high temperature gives carbon monoxide plus hydrogen. This is used for the industrial preparation of hydrogen. Okay. Then various conformations. Okay. So alkane contain carbon-carbon sigma bond. Alkane is having sigma bond. So sp3 hybridization is there because one carbon of one because hydrogen is there, and in the excited state 3p orbitals are there, so sp3 hybridization is there. Okay. Electron distribution of the sigma molecular orbital is symmetrical around the internuclear axis of the cc bond. Okay. So if we talk about the electronic current distribution of the sigma molecular orbitals, okay. Sigma molecular orbitals is symmetrical around the internuclear axis. Okay, this internuclear axis. So electronic distribution of the sigma bond along the internuclear axis is distributed. Okay, which is not distributed due to the rotation about its axis. Okay. So electronic distribution of sigma molecular orbital is symmetrical around the internuclear axis, and it is not distributed due to the rotation about its axis. Okay. This permits free rotation about CC bond. Okay, and this rotation results into the differential special arrangement of atoms in space which can change into one another. Okay, so like if CC single bond is there, so Due to the internuclear axis, the sigma bond is present. CH there. So sigma bond are same. Okay, and that is why they are having the special arrangement of atom in space. That is why they can change their orientation. And these special arrangements can be converted into one another by rotation around the CC single bond. Okay, so this single bond or sigma bond is giving the flexibility for the conformations. Okay, we have seen that various cis and trans conformations are there. Okay, so like, but it is in chiral compounds like OH and Cl are there. Okay, and if hydrogen and hydrogen are on the same piece. Okay, so like this. So this is what is our cis structure because both the hydrogens are on the same side. But if this structure will be there, OH and Cl. So then this will be our trans structure. Okay. So these are the various conformations which are there. Okay. So such special arrangements, we have seen that these are conformations or conformers or rotamers. Alkanes can have infinite number of conformations by rotation around CC single bond. Okay. So by rotation around the single bond, we can have various conformations. However, it may be remembered that rotation around the CC single bond is not completely. Okay. So it may be hindered by a barrier, okay, energy barrier of 1 to 20 kilojoule per mole due to weak repulsive interaction between the adjacent bonds. Such a type of repulsive interaction is called as torsional strain. Okay. This is what is called our repulsive. Like if I say, okay, so butane, okay, and 2-methyl propane, okay. So these are having same, same molecular formula, okay, same molecular formula, but different structure. Okay, so these are structural isomers. Likewise, conformational isomers are there. Okay, so these are the fundamental of conformation with the example of ethane. Okay, ethane molecule is our C2H6. If we observe the ball and stick model of ethane, then there can be two conformations. Okay, eclipse and staggered. So and rotate one of carbon. Okay, so if I just take this ethane molecule. And if I take the ball and stick model, okay, of ethane and rotate one carbon atom, keeping the another carbon atom stationary about CC axis. Okay, so I'm just rotating this carbon, and this carbon is my stationary. It is not rotating. Okay. We will observe that the rotations will result in an infinite number of spatial arrangements. Okay, there are various arrangements at each and every position. Okay, of hydrogen atoms attached to one carbon with respect to the hydrogen atom attached to the another carbon. Okay, these are stationary, and this carbon is rotating. Okay, so there are infinite number of spatial arrangements which can be possible. These different arrangements are better known as conformational isomers or conformers. Okay, these arrangements are known as conformational isomers or conformers. Predominantly, these can be broadly classified into two cases: eclipse conformation and staggered conformation. Okay, so they can be of two types: eclipse and staggered conformation. So, conformation in which hydrogen atom attach to two carbons area nearest to each other are known as eclipse pair. Okay, so like this. Okay, these are nearest. This one is my nearest. Okay, so Sawhorse and Newman projection formula are there for the Newman projections. Okay, so like here in the eclipse structure, and then in the staggered formation, conformation in which hydrogen atom attached to two carbon are far as possible. So like here, hydrogen atoms here they are near, so this is eclipse conformation. Okay. With respect to each other is known as staggered conformation. Okay. Staggered conformation is thus relatively more stable because the minimum repulsive force is there and minimum energy is there, therefore maximum stability is there. Okay, and therefore minimum energy is required to separate the electron cloud of CH bonds. Okay, because they are like in this staggered conformation, they are in the relatively more stability is there. Okay, because these are as far as possible. Okay, so like electron cloud to remove these CH bonds. Okay, if this CH bond is there and if this CH bond is here. So they are far apart. So the electron cloud of this partial positive and this partial positive, they are easy to separate. Okay. So minimum energy is required for the separation of CH. Okay. So in the sawhorse projection, in this kind of projection, the bond between carbon atoms is shown as a long straight line. Okay. So like this bond is there between the carbon atoms. It is shown as a long straight line. And the lower end of the line designates the front carbon atom, whereas the upper designates the rear carbon atom. So like lower end of the carbon denotes the front. This one is front and this one is rear. Okay, it is at the back. Since each carbon atom is in ethane is attached to 3 hydrogen atoms, each atom has 3 lines attached designating CH bond inclined to an angle of 120 degree because it makes a tetrahedral angle. Okay, so 120 degree. Each angle with the hydrogen is of 120 degree. Now Newman projection. Okay, so this we have seen the sawhorse projection. It looks like a sawhorse. Okay. Now Newman projection. In this projection, out of the 2 carbon atom present in ethane, one which is nearer shown by a dot, whereas the rear carbon is represented as a circle. Okay. So like if this is near, so it is represented by a dot. This is near and this is far. Okay. And that this one is far, or we can say rear. So the 3 hydrogen atoms attached to each carbon atom are represented with the help of 3 lines, either bulging out of the circle or diverging off the dotted line. These lines are inclined to an angle of 120 degrees. Okay. So either they are coming out of the circle or as a dot. Okay. So this is for the ethane molecule. This is my first carbon of which hydrogens are attached. Okay. This one. And this is my second carbon of which hydrogens are attached. Okay. So if we look at the structure of 2-butanol, okay, so these are the sawhorse projection formulas in which hydrogen atoms are apart. Okay, atoms are together, and here the hydrogen atoms are going different. Okay, so this can be a staggered conformation. Okay, this is sawhorse, and these are the Newman projection formulas. Okay. So relative stability of conformation, as mentioned earlier in staggered conformation of ethane, the electron cloud of carbon and hydrogen are as far as possible in staggered conformation. So in like this staggered conformation, let me say, the hydrogens are as far as possible. So less energy is required for electron cloud formation. So carbon hydrogen bond, the electron clouds are far apart, therefore less energy is required to break that bond. Okay. Thus, there are minimum repulsive forces, minimum energy, and maximum stability. Okay, if energy is minimum, then stability will be maximum. And minimum repulsive forces are there due to the carbon hydrogen bond is having a electron cloud is having a good distance. Okay. So on the other hand, when the staggered form changes into the eclipse form, the electron cloud on the carbon hydrogen bonds come closer to each other, resulting in increase in electron cloud reactions. Okay. So if we say that if when the staggered form changes into eclipse form, okay, so the electron clouds of the carbon hydrogen bond come closer and thus resulting in more cloud reflections. Okay. To check the increased repulsive forces, molecules will have to possess more energy and thus will have less stability. So if they are going from staggered to eclipse conformation, then eclipse conformation will have very less stability because more energy will now be required to break the electron cloud of the CH, carbon and hydrogen bonds. Okay. So to check the increased repulsive forces, molecule will have to possess more energy and thus lesser stability. Okay. As already mentioned, the repulsive interaction between the electron cloud, which affects stability of a conformation, is called as torsional strain. We have seen this, that if the repulsive interaction is there between the electron cloud, then the stability of conformation is increasing. Okay. So this is what is called torsional strain. And magnitude of torsional strain depends upon the angle of rotation about CC bonds. And this angle is also called as dihedral angle or torsional angle. So the carbon-carbon angle which is formed, the torsional angle is dependent on this CC bond. Okay. So of all the conformations of ethane, the staggered form has the least torsional strain and the eclipse form has the maximum torsional strain. Okay. Therefore, staggered conformation is more stable than eclipse conformation. That staggered conformation is more stable than eclipse conformation. If we talk about the stable. Okay. Hence, molecule largely remains in staggered conformation, or we can say that it is preferred conformation. Okay, so always the molecule would like to live in the staggered conformation. Okay, process it has not been possible to separate and isolate different conformations of ethane. Okay, because they are so much interchangeable. Okay, because there is very less value of their strain. Okay, angular strain is very less in case of ethane molecule. So that is why the various conformations are staggered and eclipsed conformations. Okay, and Chaucer's and Newman conformations are there. Okay, so here we see that if we have to structure of butane also, this will be methane, ethane, propane, and butane, and two hydrogens. So like if I just draw this structure like this, then this will be my staggered. This will be my eclipse structure. Okay? Because in eclipse structure they are so near. Okay, and if I just draw the this is my staggered conformation. Okay. Okay, so now we come to alkenes. Alkenes, we know these are double bonded when two carbons are joined by a double bond. So these are unsaturated hydrocarbons containing at least one double bond. Okay, what should be the general formula of alkenes? It is CnH2n. Okay, because it is C2H2, so it will be C2H4. Okay, because double bonds only four hydrogens will be able to accommodate. If there is one double bond between two carbon atoms in alkene, they must possess two hydrogen atoms less than the alkenes. Okay, so if two alkenes are there, so they must possess two hydrogen atom less than that of alkanes. Alkanes were having C2H4, C2H6. Okay, so here they should have C2H4. Okay, so hence general formula is CnH2n. Okay. Alkenes are also known as olefins, okay, oil forming, since the first member ethylene or ethene was found to form an oily liquid on reaction with chlorine. C2H4 plus Cl2, C2H3Cl plus HCl is M. Okay. So structure of the double bond. So carbon-carbon double bond of alkene is consists of one strong sigma and one pi bond. Bond enthalpy about 397 kilojoule per mole. And due to the head-on overlapping of sp2 hybridized orbitals, these p orbitals due to the head-on overlapping, and 1 weak pi bond about the enthalpy of 284 kilojoule per mole obtained by the lateral or sidewise overlapping of two p orbitals. Okay, this we called as the sidewise overlapping, okay, or head-on overlapping of the s and p orbitals. Okay, so this sp2 hybrid orbitals of the two carbon atoms. Okay, so first of all, like how the carbon-carbon double bond is formed by the one strong sigma bond due to the head-on overlapping of sp2 hybrid orbital, and one weak pi bond enthalpy due to the sidewise overlapping of two p orbitals. Okay, of two carbon atoms. This carbon atom, this carbon atom. So if it is making bond with the hydrogen, so this will be there, and if two p orbitals will be there, so head-on overlapping we can say, or if pi bond is formed, then it can form by the sidewise overlapping. Okay, so the double bond is shorter in bond length. Okay, double bond is shorter in bond length than the CC single. Okay, so bond length, if it is short, then it will be more stable. You already read that the pi bond is weaker due to poor sidewise overlap. Pi bond is weaker than sigma. We can say that sigma bond is strong between the two p orbitals. Thus, the presence of pi bond makes alkenes behave as a source of loosely held mobile electrons. Okay, these pi electrons are loosely held and they are the rich source. Therefore, alkenes are easily attacked by reagents or compounds which are in search of electrons. Okay, because alkenes have a double bond or a pi bond system. Okay, such reagents are called as electrophilic reagents, okay, because they are electrophilic in nature. They can readily donate. Okay. We know that nucleophiles are electron donating groups and these are electrophilic reagents. So electrophilic reagents means electron withdrawing. So electrophilic reagents means the attack of electrophile will be there on alkene because it is having a lone pair of electrons. Okay, pi electrons are there. Okay. The presence of weaker pi bond makes alkenes unstable molecule in comparison to alkanes and thus alkenes can be changed into single bond compounds. Okay. So like if weak pi bond system is present in alkenes, they are unstable molecule and thus electrophilic reaction. Okay. Electrophilic addition reaction or substitution reaction can happen. So therefore, alkenes can be changed into single bond compound by combining with the electrophilic reagent. C double bond C was there. Any electrophile attacked. Okay, and withdraw the electron withdrawing group. So alkane formation can happen. Okay. Strength of the double bond enthalpy 681 kilojoule per mole is greater than that of carbon-carbon single bond in ethane. Okay. Strength of double bond is greater than that of single. The bond enthalpy we talk about, then it is having 681 kilojoule and it is having 348 kilojoule. Okay. Alkenes contain carbon-carbon double bonds and are unsaturated hydrocarbon with the molecular formula of CnH2n. This is also the same molecular formula for cycloalkanes. Okay. The parent chain of alkene is longest chain containing both carbon atoms of the double. Now, how will look the double bond system in the alkene? So it should be the longest chain which is carrying the double. Okay. So alkenes are named by dropping the ane of the parent by adding ene. Okay. Methane was having ane, alkanes were having ane, but alkenes will have now ene. Okay. And also the position of double bond in the parent chain of alkene is indicated with the number. The position. If at the second position, the ene molecule is there. So we'll say pent 2 ene. At the second position, it is signifying that there is a double bond. Okay. So it is always indicated with a number where it is present, where the double bond is present. So the basic rules for naming alkene are for straight chain alkenes. It is the same basic rule for nomenclature of alkenes and alkanes. Okay, same suffix and prefix we have to add. First of all, we have to find the longest carbon chain that contains the both carbon of the double. Okay, so like here, this compound is not named as pentene. Okay, pentene we cannot name 1, 2, 3, and 4. Okay, so double bond is not included in the chain. Okay, so 1, 2, 3, 4, and 5. Okay, so it will include like this. So it will be methane, ethane, propane, butane, pentane. Okay, so this cannot be pentene. We cannot name this. If we have to make it pentene, then 1, 2, 3, and 4. So what we'll say? 3 ethyl. Okay, so we will start numbering with the double bond. 1, 2, 3, and 4. So 2 ethyl, but, 2 ene. 2 ethyl, but, 2 ene. Okay, so this compound is named as butene because the double bond is contained in the 4 carbon chain. Okay, so we have to look at the double bond where it is present. Okay, we can take it this one also. Same method of same, it will be same. Okay, this will be 1, 2, 3, and 4. This will be 1, 2, and 3, and 4. So same thing will be there. Okay. So start numbering from the end of the parent chain, which gives the lowest possible number to the double. Okay. So like I could have started from here, but the 4 was numbering coming over here. So I will have to give the lowest possible number. So I will start from right side. Okay. So this is giving 2, least possible. Okay. Now if I start from here, 1, 2, 3, and 4. And if I started from here, then from the left, then 3 numbering was coming, which was lowest. Okay. If the double bond is equidistant from both the ends, okay, if 3 is numbering is coming from both the ends, then we will have to look at the substituents, okay. Substituents at the lowest possible number. Then we will have to look at the substituents, okay. The double bond in cycloalkanes do not need to number because it is understood that they are in one position. Okay, double bond in cycloalkenes, if they are present, then like always if in cycloalkene it is present. So I will start numbering from here. It will be my first position. So it does not require any nomenclature. So place the location number of the double bond directly before the parent name. Okay. So like it is pent 2 in. Okay, like this. So we will have to put the location number where it is present before the parent. Okay. So the location number indicates the position of the first carbon and double. Okay. So if I'm having the double bond where it is present, it will tell us add substituents and their position to the alkenes as prefix. We have to add the main root shape. Okay, so add substituent like so before prefix means. So remember, substituents are written in alphabetical order. So if I'm having ethyl and methyl, then I will give priority to ethyl, and before ethyl, like 2-ethyl pentene. So before the parent chain, okay, pentene was my parent chain. The presence of multiple bonds is indicated by using the appropriate suffix such as diene or triene. Okay. If like I'm having this, so 1, 2, 3, 1, 2, 3, 4, 5, and 6. Because double bond was getting over here, least priority. So what I will say, 1, 3, 4, triene. Okay, hex 1, 2, 4, triene, hexene. Okay. So each of the multiple bonds receives a location number. Okay. Also, only Ne is removed from the parent alkane chain name, leaving an A in the name. Okay. Overall, the name of the alkene should look like location number of substituent, name of substituent, location number of double bond, and name of the parent chain plus E. Okay. So where the substituent is present, first of all, we'll have to look at like at the third position if any substituent is there. Okay, so 3, then nitro substituent is there, so nitro. Location of the double bond, 4. Okay, at the fourth position. Then name of parent chain, 4 pent E. Okay, like this. 4 pent E. 4 pent 3 like this. Okay, at fourth position is indicating the location number. So like 2 pentene at second position double bond is there. So one can write like this: 2-methyl 3-hexene. Second position there is a methyl group. Substituents are always given more priority. Okay. 2-methyl at the third position there is hexene. Now 3-ethyl 1-butene. Third position there is ethyl, and then 1-butene. At first position there is butene. 5-methyl 1,3-hexadiene. At the fifth position there is methyl group. Hexadiene. Hexadiene at which position? At first and third position there is ene group. Newer IUPAC nomenclature in 1993. IUPAC is International Unit Nomenclature. Okay. So International Pure and Applied Chemistry, it's a union for International Union Pure and Applied Chemistry. Okay. So updated their naming recommendations to place the location number of the double bond before the ene suffix of alkene. Okay. So like we used to write pent 1, 3 diene. But now we will have to write 1, 3 pentene. Okay, pentene. Okay. Like over here also write 1,3-hexadiene. So 1,3-pentadiene. That provides the name such as hex-2-ene rather than 2-hexene. The newer system is slowly being accepted, so it occasionally, sometimes, okay, sometimes be encountered, rejected, sometimes. Okay, naming cycloalkenes. Because there are no chain lines in cycloalkenes, the bond is assumed to number C1 and C2, and its location number is not required in the name. Okay, so if I will draw any compound over here, so it will be my cycloalkene. So this will be my C1 and C2. The direction of the number is determined by which will give the substituent closest to the double bond and the lowest number. So if substituent is there, so the numbering should start from here. Okay, 1, 2, 3. If multiple double bonds are present, it may necessarily to include their location number in the name. One of the double bond will be numbered as C1, C2, and the numbering direction is determined by which gives the double bond the lowest possible number. Okay, remaining double bonds. If one double bond is present over here, so I can start the numbering from 1, 2, 3, and 4. But no, I have to give priority first of all to the substituent. Okay, so what I will do, Okay, so on the double bond, they have already clearly stated that the direction of the numbering is determined by which will give the substituent closest to the double. The substituent should be closest to the double bond and lower number. If multiple double bonds are present, it may necessary to include their location. So substituent should be given priority. If more than one double bond are present, so 1, 2, 3, 4, 5, and 6. Okay. So if 3-methyl cyclopentene is there, so 3-methyl. Okay, so before double bond has to be given priority before the substituent. So I can make this 1, 2, 3, 4, 5, and 6. Okay, if there is a single double bond, then 1, 2, 3, 4, and 5. Substituent, I cannot write 3 over here. Substituent has to be given the priority. In 1,5-dimethyl cyclohexene, methyl group and double bond was present. So I will start the numbering from here. And 1, 2, 1, 2, 3, 4, 5, and 6. At the fifth position, there is methyl group. So I can start the numbering from here. It can be 1, 2, 3, 4, 5, and 6. But what is happening? Then the methyl, if I will start the numbering from here, then the methyl group are having the lowest number. Okay. So, but 1,5 dimethyl is here the double bond will be taken into account, like 1, 2, 3, 4, 5, and 6. So the substituent will not be given priority. Okay. So I have to take care of the both substituent as well as the alkene. So over here, in case of cyclopentene, here the alkene was given the priority. Here the substituent and alkene both were given the priority. That is why it went like this. Okay. So here nothing is there. So we can start, if we will start from here, 1, 2, 3, 4, same thing will be there in case of 1,3-cyclohexadiene. So now we are supposed to write cyclohexa 1,3-diene. So endocyclic versus exocyclic. Endocyclic bonds have both carbons in the ring, and exocyclic bonds have one carbon as a part of the ring. Okay. So definition of cycloalkanes. We know a type of alkane which has one or more ring of carbon atoms in a chemical structure. So like cyclopentene is there. So we'll start the numbering from here: 1, 2, 3, 4, and 5. Methyl cyclopentane. First of all, cyclopentane, and at first position there is methyl. If it is like exocyclic double bond, this is exocyclic double bond. Okay, because we know that here why the exocyclic double bond is coming, because it is benzene. Then if I say 1-methyl cyclopentene, at the first position there is methyl group, and there is pentene inside the ring. Okay, so the methyl group, it is endocyclic. The methyl group places the double bond. It is correct